Hello, welcome to this 16th lecture session of Database Management Systems. In the previous session, we discussed various concepts related to transaction model, and in this session we will discuss concurrent transactions and concurrent schedules and advantages and then ill effects of executing transactions in a concurrent way. First we discuss concurrent transactions, basics of concurrent transactions, transaction schedules, serial and then concurrent schedules, and need for concurrency control when multiple transactions are executed simultaneously, then conflicting operations, conflict equivalent schedule and test for conflict serializability, and view equivalent schedules and then view serializability concepts will be discussed in this session. Multi-programming in modern systems increases the throughput. That is the basic purpose of multi-programming, and this happens because the resources are shared by more than one process. That is in the case of operating systems. Similarly, in database management systems, multiple transactions are executed concurrently. That means the process in operating systems, analogous to that, the transactions here in database management systems are executed in a concurrent way. And what are the resources used by processes running in a system? It can be an IO device, or it could be RAM, it could be processor, so on and so forth, files, so on and so forth. But in database management systems, the transactions use resources which we consider which are nothing but that data items. A transaction is a collection of operations that perform a single logical operation or function in a database application, and this we have discussed in the previous class. Each transaction is a unit of atomicity. That is the basic property of a transaction. That is, either it is done in its entirety or not done at all. It is not the case that few of the instructions of a transaction are executed successfully and then remaining are not executed. That should not be the case. It is a unit of atomicity. Here for transactions we consider data items as resources, because transactions process data by accessing them from the database. When multiple transactions access data elements in a concurrent way, this may destroy the consistency of the database, and one advantage of executing multiple transactions or concurrent transactions is we are going to increase the throughput, because the data items, which are nothing but the resources for these transactions, are being used in a shared manner, but at the same time that may destroy the consistency of the database. That is why we need to be very careful when we execute multiple transactions simultaneously. Now let us have a look at what is a transaction schedule. The descriptions that specify the execution sequence of instructions in a set of transactions are called as schedules. Hence, schedule can describe the execution sequence of more than one transaction, and here if you look at this diagram, here this is called as a schedule, and this schedule has transaction 1 T1 and then transaction T2. Now these are the instructions that are part of the transaction. A transaction is nothing but a collection of instructions, and the T2 has these three instructions. Now this schedule clearly tells us, and on x axis I have transactions, on y axis it is timeline. That means this clearly tells us what instructions from which transactions are executed in what order. In this specific example, all the instructions, that is instruction 1, 2, 3, 4, 5 of transaction 1 are executed first. Once all the instructions of T1 are completed, then I take up T2 for execution. Here in the schedule, the transactions T1 and T are executed in a serial manner. That is, first all the instructions of the transaction T1 are executed, and then the instructions of T2 are executed. Hence, the above schedule is known as a serial schedule. This is called as a serial schedule. That is, a schedule may involve or contain any number of transactions, and each transaction contains some instructions. And suppose in this case I have only two transactions T1 and T2, and then if I execute T1 first to its entirety and then take up T2, or otherwise first you execute T2 and then take up T1, both these cases are considered as serial schedules. That means all the instructions of a given transaction are executed together. So this is a serial schedule. In a serial schedule, instructions belonging to one single transaction appear together. A serial schedule does not exploit the concurrency. So what is the problem with the serial schedule? Since there is no concurrent execution of the transactions, all the instructions of execution T1 are executed first, then the instructions of T2 are executed. So there is no interleaving of the instructions from these transactions, hence there is no concurrency. That means it is less efficient. If the transactions are executed in a concurrent way, then the resources can be utilized more efficiently, hence more throughput can be achieved. That is the advantage. A serial schedule always results in correct database state that reflects the real world situation. That is the basic advantage of the serial schedule. That is, if you have a serial schedule, that is when I am executing transactions one after the other in their entirety, then what happens? It is always resulting in a consistent database or correct database state that reflects the real world situation. But at the same time, what is the disadvantage? That may not be efficient, because I am not going to use the resources in a effective way or in a shared way. So that's why that is the advantage of serial schedule, that is it will result in correct database, and the disadvantage is less throughput or less efficient. When instructions of different transactions of a schedule are executed in interleaved manner, we call such schedules as concurrent schedules. This kind of concurrent schedules may result in incorrect database state. That means you have serial schedules and then you have concurrent schedules. What is the advantages of these things? Advantage of serial schedule is it is always resulting in correct database state, and it may be inconsistent. It may result in inconsistent state. That is the disadvantage of the concurrent transaction. And if you look at the disadvantage of serial schedule, and it is not that efficient. If you look at the advantage of concurrent schedule, it is more efficient, because since the resources are being used in a shared manner, that will definitely increase the throughput, hence it is more efficient. At the same time, when multiple transactions are trying to access the data items which are nothing but resources, and it may lead to inconsistency. So these are the advantages and then disadvantages of serial and then concurrent schedules. And this kind of concurrent schedules may result in incorrect database state, which is actually not desirable. And this particular schedule, which contains T1 and T2, the T1 has 3 instructions, T2 has 3 instructions. And if you look at the sequencing, first instruction 1 and 2 of T1 are executed. Before it is completed, the instruction 1 and 2 of transaction 2 are executed. Then instruction 3 of T1 is taken up, and then instruction 3 of T2 is executed. And this schedule, where the instructions from multiple transactions or different transactions are being executed in an interleaved way. Okay, this is called as a concurrent schedule, and this may result in incorrect database state, and the advantage is this will definitely increase the throughput of the application or the process. Then what are the other ill effects of concurrent schedules? That is, when you execute the transactions in a concurrent way, what are the various problems that we encounter? The first problem is the lost update problem. The second problem is temporary update or dirty read problem. The third problem is the incorrect summary problem. And always we understood that when multiple transactions are there, the executing them in a serial fashion always results in correct database state, and when you execute them in an interleaved fashion, then it may result in incorrect database state. Okay, and that's why when you have a concurrent transactions, that is when there are instructions of multiple transactions are being executed in an interleaved fashion, somehow if the final result of that concurrent schedule is same as some serial schedule, that is executing T1 and T2 or the transactions in that schedule in a serial fashion, then that kind of concurrent schedules are more preferable, because I am not going to face any problem with respect to concurrency, and at the same time, because of the concurrency, I am going to increase the throughput. That's why if you have two transactions T1 and T2, always the result, when I execute T1 first and then T2 next, or T2 first and then T1 next, then only it will always result in correct database state, and even then the instructions are being executed in an interleaved fashion, still the final result of that concurrent schedule is same as the serial schedule, then it is acceptable for us, because it will not create any problem with respect to concurrency, and at the same time we can increase the efficiency. Now let us to have a better understanding about these problems, that is lost update problem, temporary update problem, and then incorrect summary problem. Let us have a look at this example. In this case, I have T1 and T2. There are data items X and Y and some values M and N. T1, what it does, this is the timeline, that is it is a concurrent schedule, because the instructions from T1 and T2 are being executed in an interleaved fashion. T1 is reading the data item X, then it is modifying the data item X is equals to X minus N. Then T2 reads data item X and then it is modifying the data item X is equals to X plus M, and then the modified value of T1 is returned to the database, then it is reading Y, and then the modified value of X by T2 is returned to the database, then Y is modified by T1, Y is returned by T1. Then if you carefully observe that T1 has modified the data item, if when it is executed T1 first and then T2 next, what happens? When T2 is reading the data item X, it must read the value of X which is modified by T1, but unfortunately here, because of this concurrent execution, what is happening? T1 has modified the data item X, and then it has, before it has written the modifications to the database here, the T2 has read the data item X and then that has used data item X for its manipulation or processing. So that's why then immediately what is happening, T1 is writing the data item X to the database, and then later T2 is writing data item X. Finally, the T2 was supposed to use the data item X which was modified by after modification by T1, but unfortunately because of concurrent execution, T2 is reading the data item X before the T1 finally writes the modified value to the database. Hence T2 is always reading some incorrect data, and then whatever update that has been made by the T1 is immediately overwritten by the transaction T2. Hence the update made by T1 on data item X is lost, it is overwritten by T2. So this is called as lost update problem. Now to have a better understanding of this, what we can do is we can assume some values for X and Y and then M and N, then we can see what is the final result of executing this concurrent schedule and what could be the final result of executing T1 first and then T2 next. Definitely there will be a difference. That means the concurrent execution of these two transactions is not going to reflect the real world situation. Hence that will leave the database in incorrect state, and this problem is known as the lost update problem. Now let us try to understand what is the temporary update problem or dirty read problem. This is also called as dirty read problem. I have T1 and T2, this is the timeline. Of course it is a concurrent schedule because the instructions from T1 and T2 are being executed in a concurrent way. First 3 instructions of T1 will be executed, next immediately 3 instructions of T2 will be executed, then the last instruction of T1 is executed. And here the result should be same as, if the result of this executing this concurrent schedule is same as T1 first and then T2 next, then I don't have any problem. But unfortunately here what is happening, let us assume that there is a data item X and then first T1 is reading that data item, it is modifying that data item and then it is writing the value of X to the database, and immediately it is returned to the database. Immediately T2 is reading that data item and it is modifying the data item X and then it is writing the data item X. But let us assume that unfortunately after executing first 3 instructions, the transaction T1 has failed. The transaction T1, there is a problem, system crash or something has happened and the execution of T1 has failed. Not system crash, because of some problem T1 could not continue further. Then according to our transaction model, a transaction is a unit of atomicity. Either it is executed in its entirety or not done at all. and in our case the first 3 instructions are executed, last instruction of T1 is not executed. So the third instruction of T1 has already modified the data item X on the database, and that modified item has been taken up by T2, it is read by T2. But due to the failure of T1, what should happen? The modifications that have been done by T1 should be removed or nullified, or it is rolled back. The T1 should be rolled back. That is, I will have to remove the effects done by these half done transactions. But unfortunately, what has happened? I will roll back. Now let us assume that I will roll back. The third instruction, the data value X item, the value is actually 20. Let us assume that the T1 has modified this to 10, and immediately after modification T2 has read that data item, it has read it as 10. But so when I notice that the transaction T1 has failed, I will roll it back to old value, that is 20. Now if you carefully observe, because of this concurrency and the old value, that is actually the incorrect value that has been modified by T1 and which has been rolled back by on failing of this transaction T1, that has been read by T2, which is not correct. When T1 is rolled back, the value of X should become 20. Then if I am executing T2 next, the T2, if at all it is reading the data item X, it should read it as 20. But unfortunately, because of this concurrency, it has read the data item X as 10, which is not correct. This is called as dirty read problem or temporary update problem. Okay, so whatever updates that have been made by the half done transaction T1, that was only a temporary update, and this updated value has been taken up by T2. So which is a temporary value, and then which is taken up by T2, and that gives the incorrect state of the database. Hence it is a problem which is called as dirty read problem. The next problem, due to this concurrent execution of transactions, is incorrect summary. Let us assume that T1 is there, T2 is there, and T1 is trying to modify the data item X, and T2, which is another functionality, which is another transaction, which is trying to compute the sum of the data items. Let us assume that the data items are A, X and Y, so on and so forth, and here what is happening? First sum is equals to 0, and T2 is reading data item A, and it is adding A to sum, that is sum is equals to sum plus A, and then immediately X has been modified by T1 and it is written permanently onto the database by T1, and immediately the T2 is reading that value. That means if you look at this, the effect should be same as T1 first and then T2 next. Unfortunately, what is happening? That is, when you execute T2 either in the beginning or after, either before T1 or after T2, then what happens? The no other modifications to the data items that are considered for these aggregate operations should be modified by any of the transactions. But unfortunately, when T2 is computing the sum, that is the aggregate of some data values A, X and Y, in between the transaction T1 is modifying the data item value X, and sometime later, and this may modify the data item A. That means some data items have been considered by T2 before they are modified, and some data items have been considered for aggregating operation by T2 after they have been modified by some other transactions. That is why that will always result in incorrect summary. The T2 reads X after the value N is added to the X, and which leads to the wrong summary, and these are the problems with concurrent execution of the transactions. The first problem is lost update problem, second is temporary update or dirty read problem, and the third is incorrect summary problem. That means the advantages of these concurrent transactions is not coming free of cost. That may lead to inconsistencies. Hence, while executing these transactions simultaneously, we need to be very, very careful. It is desirable that a schedule after execution must leave the database in a consistent state. That should not lead to inconsistency. The result of a concurrent execution must be same as the result of executing a transaction in a serial way. So that is very, very important desirable property. And if you go back to this schedule, okay, this is a concurrent schedule, and here T1 and T2 are being executed in a interleaved fashion, and if the final result of executing this is same as executing T1 first and then T2 next, or executing T2 first and then T1 next, then I can call that the result of this concurrent schedule is same as executing the transactions of that schedule in a serial way. So that is more desirable. If the result of a concurrent execution is same as the result of a executing transactions of that schedule in a serial way, then that is more desirable, and I am going to achieve the throughput, increase the throughput. At the same time, I am also taking care of the consistency of the database, because the serial execution of transactions will never result in incorrect state of the database. A concurrent schedule whose result is same as that of a serial schedule is known as concurrent serializable schedule, or we simply say that it is a serializable schedule. That means the result of a concurrent schedule must be same as executing the transactions of that schedule in a serial fashion, then it is called as a serializable schedule. Okay. Now we will look at other important notions like conflicting operations and conflict serializability. If we consider transactions T1 and T2, the order of read operations on any data item does not matter, because I have transactions T1 and T2 when they are being executed in a concurrent way. If I have some data item X, if both of them are just reading the data value, then I don't have any issue, because just reading the data item will not create any problem, hence it does not matter as far as the consistency is concerned. Okay. T1 is reading the data item Q. This is how we should read this. T1, that is transaction 1, reading the data item Q. T2 reading the data item Q. There is no problem. If you consider this pair of operations by two different transactions T1 and T2, it will not create any problem. Similarly, T2 reading the data item Q and then T1 reading the data item Q will also not create any problem, because if you look at this pair of operations, both of them involve same data item, at the same time both of them are only read operations. The result is same and does not lead to any conflict. Here the Q is the data item, but when you take the pair of operations on the same data item and these operations belong to two different transactions, and if at least one of them is a write operation, then it creates problem. That is, they are called as conflicting pair of operations. They are conflicting operations. Okay, if you consider this, T1 reading the data item Q and T2 writing the data item Q, if you consider this pair of operations, the data item is same and T1 and T2 are the transactions, and T2 is writing, T1 is reading. So it is a conflicting pair of operation. Similarly, and if T2 is doing this first and then T1 is doing this next, then also it is a problem. Same data item, two transactions 1 and 2, one is writing, another one is reading. Hence, if you take a pair of operations from two different transactions on a same data item, if at least one of them is a write operation, then I can say that that pair of operations is conflicting pair of operations. Here the I stands for, in this case the I stands for the instruction, and I and J are the transactions. That is, if you carefully read this, so it is same as what I have described just now. At least one of them should be a write operation on the same data item, and then it is known as a conflicting pair of operations. Hence it is evident that we can swap non-conflicting pair of operations of a concurrent schedules, and it will not affect the final result. It will not affect the final result. Suppose if this is the concurrent schedule, and then if I find two operations, operation 1 from T1 and then operation 2 from T2, if they are non-conflicting, that is, if there is no problem, if they are on different data items, there is no problem, they are non-conflicting, and if both of them are reading, then also there is no problem, they are non-conflicting. But if both the operations from two different transactions are on the same data item, and if at least one of them is write operation, then they are considered to be conflicting pair of operations. And if they are non-conflicting pair of operations, even then I swap the order of these things or sequence of these two, then it is not going to change. Suppose there is a schedule like this T1 and T2, and I have two operations by T1 and T2. First T1 is reading Q, and then second T2 is reading the data item Q. It does not matter. If I swap this and then create a new schedule wherein T2 is reading the data item Q first, and then T1 is reading the data item Q. I could swap this. If you consider these two, though they are on the same data item and both of them involve only the read operations, that is why they are non-conflicting pair of operations. When I find a non-conflicting pair of operations in a concurrent schedule, I can swap the order of these instructions, so there is no problem. Once swapping, first executed is the read operation of T2 and next one is the read operation of T1. So hence we can swap non-conflicting pair of operation. Now let us have a look at this example. I have a concurrent schedule. T1 reads, this is T1 reads A, writes A, T2 reads A, writes A, T1 reads B and writes B, and T2 reads B and writes B. And if you carefully, this is S1, let us consider that this is the schedule S1 which involves two transactions, and these transactions they try to access the data items A and B in a concurrent way. Now if you carefully observe and consider this pair of operations, that is, let us consider these two, and this is a this is a pair of operations from T1 and T2, and if you carefully observe, this is writing A and this is reading B. When these operations involve different data items, then they are non-conflicting pair of operations, then I can swap them. After swapping this pair, the result is this one. The resulting schedule is S2. That means that this one has gone down and this has gone up. So this is the schedule. Now this S2 is result of swapping a pair of non-conflicting operations in S1. Hence I call S2 as conflict equivalent to S1. This is known as conflict equivalent schedule to S1. Okay. If you now carefully observe, if you consider this pair of operations, both of them are on different data items. This is on A, this is on B, and at the same time both are reading. Hence they are non-conflicting pair of operations, and if I can swap them. If I swap them, this will go up and this will come down. So this is the resulting, S3 is the resulting schedule. So S3 is a conflict equivalent schedule for S2 and S1. Okay, now if you observe these two operations of T1 and T2, both of them are actually working on different data items. Hence they are non-conflicting pair of operations from T1 and T2. I can swap them. While swapping, I take this up and then bring this down. Then what happens? The result is this one. The result is this schedule. S4 is the conflict equivalent schedule to S3, S2 and S1. And if you carefully observe, the S4, which is a conflict equivalent schedule of S1 and is also a serial schedule. Why it is a serial schedule? Because all the instructions of T1 are executed first and then only the instructions of T2 are taken up. That means if you carefully observe, the result of executing the concurrent schedule which is given in this one, that is S1, is same as executing the transactions T1 and T2 of the schedule in a serial way. That is why though it is a concurrent schedule, executing this will not lead to any inconsistency. Hence this is more desirable, and this concurrent schedule is going to use the resources in a concurrent way or shared way, and at the same time, since the result is same as a serial schedule, that will not create any inconsistency related problems. Hence this is more suitable and it is more desirable, and this schedule is known as a serializable schedule. The concurrent schedule which is shown in the previous example, that is S1, is serializable because whose result is same as a serial schedule that involves the same transactions and same instructions. And S4 is also known as conflict serializable or conflict equivalent to S1, and which is also known as conflict serializable schedule. And there is one conflict equivalence. If a schedule S can be transformed into a schedule S dash, it is S dash, by a series of swaps of non-conflicting instructions, we say that S and S dash are conflict equivalent. Further, we say that a schedule S is conflict serializable if it has a conflict equivalent, if it is conflict equivalent to a serial schedule. The same thing has happened in the previous example, that is S1 was the concurrent schedule, and then S4 is a conflict equivalent schedule for S1, and fortunately it happened that the S4 is also a serial schedule. Hence, S is a conflict serializable schedule. In our example, S4 in the example is a serial schedule and is conflict equivalent to S1. Hence, S1 is a conflict serializable schedule. And if a concurrent schedule is a serializable schedule, then we can without any apprehensions we can execute that schedule to increase the throughput. At the same time, we will not have any problems as far as the inconsistency is concerned. If you look at this schedule, it is a concurrent schedule because I have transactions T1 and T2, and they are being executed in a interleaved fashion. And let us assume that this is Q, which is the data item, and it is reading the data item Q, and then T2 is writing the data item Q, and then he is writing the data item Q. And is there any swapping possible here? If you consider this pair of operations, both of them are on the same data item, and at least one of them is write operation. Hence, they are conflicting pair of operation. Swapping of these operations is not possible. And now, if I consider this pair of operations, both of them are on the same data item, and at least one of them is a write operation. Hence, swapping is not possible. And if you carefully observe, you can conclude that no swapping is possible, and this concurrent schedule has no other conflict equivalent schedule, that is no other swapping is possible. Hence, it has no conflict equivalent schedule. Hence, it is not serializable. This schedule given here in this example, it is not serializable. When it is not a serializable schedule, then what does it mean? When you execute that, you may increase the throughput. At the same time, it may lead to inconsistency. Hence, we need to be very, very careful. And now, let us have a look at the technique using which we can test whether a given schedule is a conflict serializable schedule or not. Let S be a schedule. We construct a precedence graph. We are going to do this by drawing a precedence graph. Each transaction participating in the schedule will become a vertex. It is a graph which contains vertices and then the edges. And then what become nodes? Each transaction that is taking part in the schedule becomes the node here, and the set of edges consist of all edges from Ti to Tj. That means, if I have a transaction Ti and a transaction Tj, I can introduce an edge from Ti to Tj when at least one of the following conditions is satisfied. If Ti executes write on data item Q before Tj executes read on data item Q, that is same data item. Otherwise, if Ti executes read on data item Q before Tj executes write on data item Q, or Ti executes write on Q before Tj executes write on Q. That is, if there are two transactions Ti and Tj, and if Ti is reading something or writing something before this fellow does, then on the same data item, then I can introduce an edge from Ti to Tj in the precedence graph. This graph is known as a precedence graph, where the transactions that are taking part in the schedule, they become the nodes, and the edges will be Ti to Tj when this one of the following conditions is satisfied. At least one of these is satisfied, then I can introduce an edge. Okay, let us consider this schedule where I have T0 and T1. It is a concurrent schedule because the instructions are being executed in a interleaved fashion. And if you consider this, what is happening? T0 is reading the data item A before T1 writes the data item A. hence I can introduce an edge from T0 to T1, and at the same time if I consider these two, T1 is reading data item A before T0 writes the data item A, hence I can introduce an edge from T1 to T0. You keep on introducing edges between these nodes which are representing the transactions that are taking part in the schedule. At any point of time, if you see a cycle, then you stop your algorithm and declare that it is not serializable. Hence, in this example, I could see a cycle, one edge is from T0 to T1 and another edge is available from T1 to T0, there exists a cycle. Now I can declare that this schedule is not serializable, and then if you carefully observe, there is no way that I can swap these two, so that I can take all this up and then bring all this down. At the same time, I cannot swap these two, because so as to bring all this down and then take this up, hence it is, and similarly I cannot swap these two so as to take these instructions up and then bring this down, hence the swapping is not possible, and hence it is not a serializable schedule, and when you execute this concurrent schedule, that may lead to inconsistencies. Let us consider this schedule what we have considered in the first case, that is where I had S1, S2, S3 and S4. From S1, after swapping a pair, I could get S2, and that is there in this example, that is this example. Yeah. From S1 I could get S2, and from S2 I could get S3, and from S3 I could get S4 by series of swappings of non-conflicting pair of operations, and ultimately I could see that S4 was a serial schedule, hence I declared that S1 is a conflict serializable schedule. Now let us try to check the same thing using this precedence graph, the technique we are using to identify whether a given schedule is serializable, conflict serializable or not. T1 and T2 are there. I have this should be, let us consider it as T1, and this is T0. First schedule is T0 and second one is T1, hence I have T0 as one node and T1 as another node. Now can I draw an edge from T0 to T1? By considering this pair of operations where T0 writes data item A before T1 reads the data item A, hence I can introduce an edge from T0 to T1, there is no problem. And similarly, if you consider this pair of operations, still I can introduce the edge between T0 and T1 only. It is already there, I do not have to worry about that. And then if you consider these pair of actions, that is this pair of operations, still I can introduce an edge from T0 to T1 alone. Can we see any situation where I can draw an edge from T1 to T0? Let us consider it as T0 and this is T1. There is no way that I can draw an edge from T1 to T0. T1 to T0 edge can appear when the T1 is reading some data item before the same data item is written by T0, or T1 is writing the data item before T0 is reading or writing the data item. But there is no such situation, hence always I can introduce number of edges between T0 and T1 only due to different pair of operations. I do not see any situation where I can introduce this edge, this is not possible. Hence after exhausting all the possibilities, I could see that there is no edge from T1 to T0, hence no cycle exists in this example for this concurrent schedule. Hence I can declare that this schedule is concurrent conflict serializable schedule, and the same thing has been proved in the previous example, that is when we tried to swap them manually, this also proved that S1 is a conflict serializable schedule and which is equivalent to S4 and which is a serial schedule. Hence using this precedence graph I can find out whether a given concurrent schedule is serializable or not. And if you have this kind of mechanism, if a concurrent schedule is there and if you find that it is not it is serializable, it is serializable, and then you can happily execute that schedule, because it will not create problems and at the same time you will enjoy the increased throughput. So what is a precedence graph? It has nodes and edges. All transactions that are taking part in the schedule will become the nodes, and I can introduce an edge between Ti and Tj when following conditions, either at least one of the following conditions is satisfied for Ti and Tj. If there is a cycle, it is not serializable, and if there is no cycle, I can declare that it is conflict serializable. A schedule S is serial if for every transaction T participating in the schedule, all the operations of T are executed consecutively in the schedule. That is serial schedule definition. Otherwise, it is known as a non-serial schedule or concurrent schedule. Serializable schedule. A schedule S is serializable if it is equivalent to some serial schedule of the same transactions. Okay. Hence, a serial schedule is not same as serializable schedule, but the result of serial schedule is same as a serializable schedule. That is very, very important point to be noted. Two schedules are called result equivalent if they produce the same final state of the database. Conflict equivalent. Two schedules are said to be conflict equivalent if the order of any two conflicting operations is same in both schedules. And in the previous example, S1 and S2 were conflict equivalent. Okay, because the order of conflicting operations in both of them is same, but the order of non-conflicting operations has been modified. And what is conflict serializable? A schedule S is said to be conflict serializable if it is conflict equivalent to some serial schedule S dash. Being serializable, one important point to be noted here is being serializable is not same as being serial. Okay, a serializable schedule is a concurrent schedule, whereas a serial schedule is a schedule where all instructions of a transaction appear together, and being serializable implies that the schedule is a correct schedule. That means if it is a serializable schedule, means it is a concurrent schedule, but the result is same as executing a serial schedule, and it will leave the database in a consistent state. The interleaving is appropriate and will result in a state as if the transactions were serially executed, yet we will achieve the increased throughput, or we can achieve the efficiency due to concurrent execution, where the resources are being used in a concurrent way, shared way. Now we have another notion called as view equivalent schedules. Two schedules S and S dash are said to be view equivalent if the following three conditions are satisfied. All the three should be satisfied. This is condition 1, condition 2 and condition 3. The condition 1 says that for each data item Q, if the transaction Ti reads the initial value of Q in S, then the transaction Ti must in schedule S dash also read the initial value of Q. For each second condition is for each data item Q, if the transaction Ti executes read on Q in S and the value produced by the Tj, if any, then the transaction Ti must in schedule S dash also read the data value Q that was produced by Tj in the other schedule also. Similarly, for each data item Q, if the transaction writes the final value of data item Q, and that should be the transaction in the other schedule that will be writing the final value of Q. If all the three conditions have been satisfied, then I can say that S and S dash are view equivalent. Note that every conflict serializable schedule is view serializable, but not all view serializable schedules are conflict serializable. This is very, very important point to be noted with respect to conflict serializability and then view serializability. Hence, in this session we discussed what are concurrent transactions, what is a concurrent schedule, what are serial and then concurrent schedules, what are the properties of such schedules, and we have seen why concurrency is desirable, because we can increase the throughput. At the same time, why concurrency control is needed in the database management system, that because it may lead to some problems, that is lost update problem, dirty read problem, incorrect summary problem. Because of these problems, we will have to have better control over the concurrency. When we execute the transactions in a concurrent way, we need to have some control, so that that will not lead the database to some incorrect state. Conflict equivalent schedules and its importance we have seen, and then test for conflict serializability using precedence graphs are also being discussed in this session. Finally, we discussed what is a view serializable or view equivalent schedule. Thank you very much.